Okay, now that we understand the idea behind Young's double slit experiment, we have a few things that we need to precise. First, remember the wavelength of light. This is something 10 to the minus 7 meters. Okay, a millimeter, this is about a millimeter. It's 10 to the minus 3 meters. So this is, we are talking about, let's see, 10 to the 4, that's 10,000th of that. 10,000th of that is not going to be something that's easily visible. Now, why am I discussing this? Because what we said previously, to have constructive interference, the path difference between the two light beams is going to be lambda, twice lambda, 3 lambda, and so on. Now, notice, lambda is a very small number. Under normal conditions, we are not going to be able to see these things very easily. So what do? We have a setup where we start with a slit separation. Here's our slit separation. If we label it as D, we start with a slit separation. It has to be larger than the wavelength of the light that we are dealing with. The slits are not going to be separated by a large distance. It's going to be a small distance, slightly larger than the wavelength of the light, but the screen, we place it quite a distance away from the slits, okay? Very far away from the slits. And of course, the screen separation is going to be much larger than the slit width. When we increase this distance, we should be able to see the variations here easier. Again, all what we need to have to move from one bright constructive interference fringe to another bright constructive interference fringe is for the bottom beam to move a distance of 1 lambda more. That's all what's needed. That's the path difference. Now again, remembering that we have a large distance L. Focusing on the two beams. This is the top beam and this is the bottom beam. If the distance L is very large, this beam and this beam are very close to each other. It's going to be very difficult to notice any difference between them. Okay, if you follow me, what I'm trying to say, it's going to be very difficult to distinguish between the two beams if L is large enough and if D is small enough. What does that mean? For example, if I consider the angle that that beam is going to make with the horizontal, and we call it theta, this beam is going to be making essentially the same angle theta. That's first one approximation, which is a very valid approximation because this distance is very tiny compared to this distance. Okay, now, so once we agree on that, what's the difference in length between this path, the top path, and the bottom path? The difference in length is this little bit here that's labeled in red here. Now, that path difference, to try to calculate it, we are going to zoom into that small area here and approximate it by this right angle triangle here. Now, the hypotenuse for that triangle is D, the separation of the slits. And the opposite side is going to be our path difference. Now, the thing here is a little geometry. If this angle here is theta, and if this angle here is 90 degrees, and this angle here is 90 degrees, that makes this angle also be in theta. Okay, now, once we agree on that, what's my path difference? Since it's the opposite to the angle, it is just d sine theta. Now, what's my condition for constructive interference? That the path difference is equal to 0, or 1 lambda, or 2 lambda, or 3 lambda, or 4 lambda, so on. In this case, we can rewrite it as the path difference, which is our d sine theta, equal to m lambda, where m takes the values 0, 1, 2, 3, whatever. Condition for destructive interference, same thing. My path difference d sine theta is going to be an odd integer multiple of lambda, lambda over 2. How do we get that? M plus 1/2 times lambda. When m is equal to 0, this term is equal to 1/2, so it's 1/2 lambda. When m is equal to 1, that becomes 3/2 lambda. When m is equal to 2, that's 5/2 lambda, and so on. So these are my condition for interference. Okay, I'm going to add a small twist to this and label the thetas, the angle, because the angle for the first bright fringe is going to be different than the angle for the second bright fringe. So what I'm going to do, I'm going to, instead of saying theta, I'm going to say theta sub m. Theta sub m. D sine theta sub m is equal to m lambda. Okay, here I'm using n's instead of m's. Same idea. D sine of theta sub n is equal to n lambda. That's my my condition for constructive interference. Quite often we'll be interested in where on the screen I'm going to have the maxima. And sometimes I'm going to be interested in the separation between two consecutive maxima on the screen. So to do that, we are going to also remember a little bit of geometry. Okay, for example, if again we look at the setup, remember that our distance is L. If we call here Y the position for my maximum, then I have a right angle triangle approximately with the hypotenuse being this distance. Now, Y is going to be just L sine theta. Y over L, L tangent theta. Y over L is your tangent. So Y is equal to L tangent theta. Okay. However, for small angles, tangent theta is approximately equal to sine theta. So my d sine theta is actually d y over L. Now rearranging that a little bit gives me this equation here for the position for the various maxima. So the maxima are given by yn for n equals 0, that's the central maximum. N equal 1 is going to be lambda L over D. N equal 2 lambda twice lambda L over D, and so on. Another equation I didn't write here, but that's worth looking into, the separation between the maxima, which is in general yn plus 1 minus yn. The maximum occurring at the order n plus 1 minus the maximum occurring at the order by n. So that one, the way I'll find it, I write the equation when for n here I have n plus 1, n plus 1 lambda L over D, minus, I write the equation for that term being just n, lambda L over D. If I complete the operation there, all what I will get is lambda L over D. And that's a very interesting equation because actually it does not depend on n. it does not depend on where am I on the screen here. It tells me that the separation between two bright fringes is going to be the same throughout the screen. And it also tells me it's going to depend on the wavelength, it's going to depend on L, how far the screen is, and it's going to depend on the slit width. Now, it tells me the further L is, the further I put my screen, the more spread out the fringes are going to be. The bigger the wavelength of the light, the more spread out the fringes are going to be. And then the shorter or the smaller is the separation of the slits, the further away the fringes are going to be. Okay, I could go through the same analysis for destructive interference. Remember our equation. Remembering that y over L is tangent theta, and we have a very small angle here because it's a large L. So then we get the positions for the dark fringes or destructive interference are given by this. Yn is 2n plus 1 over 2 lambda L over d, where n takes the value of 0, 1, 2, and so on. Okay? So we have the positions for constructive interference, the separation of two bright fringes, and the positions for destructive interference. We have two equations for each. Okay, a small question here. What if we take a double slit setup and we see some fringes here, bright fringes like we have seen in a previous slide, and then we take the whole setup and put it in water? What's going to happen? Is the separation between minima and maxima, is it going to increase, decrease, or stay the same? Okay, for that, let's try to remember our separation equation, lambda L over D. Okay, so our separation, delta Y, is lambda L over D. So what are we doing when we immerse everything in water? Light is going to travel slower. As we discussed earlier, light will travel slower. Frequency is not going to change. The color is not going to change. But the wavelength, remember the equation as well, lambda is equal to V over the frequency. The wavelength is going to decrease. So suddenly I have a smaller wavelength of light here. If I have a smaller wavelength, but I have a smaller here, so my fringe separation is going to decrease. A decrease in lambda results in a decrease in the slit separation. Okay, one last thing here. What if we use different wavelengths of light? Excuse me. Remember the equation again. Delta Y, lambda L over D. Okay, so what does that mean? Okay, if we go blue light instead of the green here, what do I get for blue light? Blue light, I'm going to have fringes whose separation is less than the fringes for the green. Okay, I'm just giving an approximation here. So this is going to be my middle fringe. This is my first order. This is my second order. This is my third order for the blue. You notice here, they don't happen at the same place as the green one. Now, what about red, which is a bigger wavelength? Red is going to happen a little after. So this is for red. Okay, let me see. Probably I can change color. Okay, for red, it might be here, and then here, and then here. I'm just giving approximations here. But the middle one is still going to be here. Okay, in this computer calculation from this gentleman from where I got the picture here, he has a computer calculation. So if we use white light, for example, in the middle, we are going to have all colors adding up. But then the fringe for the blue is going to be narrower than the fringe for the green, which is going to be still narrower than the fringe for the red. And that's why you see the colors here with some red coming out. And then what do we get? The blue given constructive interference. And then red the further out. In between you have mixtures, the places where they are going to add up. And you get a more complicated pattern as we go on. Okay, again, the middle one is white, all of them adding up, and then that first bright fringe, its borders are going to be the red one, because it's the largest wavelength we see. And then we are going to start seeing the bright fringe for the green, and so on.